Okay, welcome back. Today we're going to talk about arranging networks and trees, and this is chapter 9 in Munsner's data visualization textbook. This is a pretty short lecture for this week, so we won't go too long, I don't think. So we start out as always with the big picture, and again, this gives an overview of the entire chapter. And so here you can see there are three major ways to arrange network data. Network data are data items that have connections to one another. For example, I'm a faculty member who reports to the Dean of the College of Natural and Health Sciences. The Dean of the College of Natural Health Sciences reports to the Vice Chancellor for Academic Affairs, who in turn reports to the Chancellor, who in turn reports to the President of the UH system, and you can keep going from there. And so those can be represented as trees. They can also be represented as node link diagrams that are more general, such as graphs or adjacency matrices. And last but not least, we have enclosure marks. And I should mention adjacency matrices are frequently useful in showing things like airline routes and for processing graphs in computer science algorithms. So let's take a look at node link diagrams. And these are the most common way to depict networks and trees. And so the points or circles are the nodes, and lines can be used for links, although they're frequently equal distant. You can also use space to show depth if you want to use more channels, but typically they tend to be equidistant, at least in computer science visualization. Node link diagrams can also be done in a radial layout. And the topology of a network is the direct and indirect connections between the nodes and the number of hops between them. And I will add the radial layout looks pretty cool, but most computer science students are used to the triangular or vertical model that you see at the top. Another technique is force-directed placement, and this is also known as spring embedding, energy minimization, or nonlinear optimization. So nodes have a tendency to push away from one another, but if you have a link between them, then that acts like a spring that draws those endpoints together. And so these are dynamically moving. This one's fairly simple to implement and easy to understand. The weakness is it's non-deterministic. You can get kind of different graphs with each run of the system. And the randomness can lead to isolated relationships from time to time, and there are some issues with scalability. And as a final note, you can sometimes fail to settle and bounce around if you don't put in a terminating condition or terminate it after a certain amount of time. The other thing to be careful of is hairballs, and too many overlapping edges produce a structure called a hairball without too much visible structure. Here we can't really see what's going on. I can't really see the connections outside of the very far edge of the graph, but inside we would just assume that most things are likely connected to one another. And this is really, really difficult to form any type of conclusions with. So, we don't want too many of these overlapping edges, and we have to be careful as to how many links we're showing. Another technique is for encoding network data is matrix or graph view. The nodes are laid out horizontal and vertical in a square region, and the links between the nodes are shown by coloring a mark in the cell that's adjacent between the row and column in terms of the matrix view that you see down in A. So here we can see purple is connected to orange, and when you cross-index the purple and the orange, you can see that those two squares are actually colored in. So that indicates there's a relationship between them. And you could do this with either one-way or two-way in terms of directions. That would give you the matrix view. So the node link is the one shown at the top, and the matrix is the one shown at the bottom. The node link is the most popular, and it's extremely intuitive for very small networks. So it's great for path tracing and other topological tasks. But as it gets larger, you have a tendency to kind of get those hairballs or too many connections, and it becomes difficult to read. The matrix is great for perceptible scalability. and it's actually one of the easier tools for implementing graph algorithms, but it can take up more space than jagged arrays or linked lists implementations in terms of programming. That being said, as visualization is predictable use of space. Adding a new item or a new link doesn't mean redrawing the entire thing. It's easy to estimate how much space you need because it's an n by n matrix, but it's not as familiar to people, and it can be really hard to see what the topology or the underlying structures are. Another technique for visualizing the network data in trees is containment or hierarch marks, and these can show more than one connection. So in this, we can show more than one connection, and all the children are enclosed in an area allocated to the node. So this second figure encodes the first to show the individual ones inside the larger boxes are the children of those nodes. And so those are contained. They're fenced in by their the ones that actually contain them. And so this is another way of visualizing that type of data. Compound network is a combination of network and tree. This is another visualization technique. The example that you see here is known as a grouse flock, and that was developed by Munzner. Here we can see the hierarchy graph, the edges between those hierarchy graphs, if they exist, or just within the individual hierarchy graphs. And there are links that have the pairwise relationships as well as the hierarchy and the containment for these compound networks. And that's it. Thanks so much for watching.